So, what if I told you that a single mathematical clue could unravel a really complex mystery? Well, today, we're driving headfirst into a linear algebra whodunit. Here, transformations and matrices are our evidence, and the hidden variable, well, that's our prime suspect. So, let's get our detective hats on and start the investigation.
Right at the heart of our mystery is this one elusive variable, A. It's hiding in plain sight within our evidence. And here's the kicker. There is only one value for A that's going to make everything click into place. Our job is to follow the breadcrumbs, rule out any red herrings, and unmask our culprit.
All right, let's open up the case file. First, we'll dust the evidence for prints. Then, we'll use a crucial clue to narrow down our list of suspects. After a thorough interrogation, we'll see how finding A unlocks the entire rest of the puzzle. This is a full-blown investigation, and you're coming along for the ride.
Every good mystery has a crime scene, right? Ours is the world of linear transformations. We've got two key players, S and T, and their combined operation, ST. You can just think of them as a series of actions performed one after the other. And A, well, A is the unknown element that's pulling the strings behind the scenes.
Here they are, our two key pieces of evidence. We've got the matrix for the combined transformation ST and the matrix for the transformation S. And notice, our suspect, A, is embedded in both of them. The entire case really hinges on figuring out the relationship between these two.
And this is our smoking gun. It's like a cryptic note left at the scene. It says the dimension of the image of S is less than the dimension of the image of S. Now, in simple terms, that just means the combined operation is kind of squishing space more than the first operation does on its own. This single clue is the absolute key to cracking this case.
So how in the world do we decipher this thing? We are about to translate this clue from the abstract world of dimensions and images into a concrete, solvable equation. Get ready, because this is where we get our first big break in the case.
Okay, so let's follow the logic here. The clue tells us that ST is squishing space, which means information is being lost, so it's not a perfect one-to-one mapping, or what mathematicians call an isomorphism. Now, for a square matrix, not an isomorphism is, just a fancier way of saying it's not invertible. You can't perfectly undo it. And what's our go-to test for invertibility? The determinant. If a matrix isn't invertible, its determinant has to be 0, period. So, we roll up our sleeves and we calculate the determinant of that ST matrix, with our variable A still right there inside. And after all the number crunching, we are left with this beautifully simple expression, A squared minus A. And since we know that determinant has to be 0, we're suddenly left with a pretty simple equation to solve. I mean, this is a huge turning point. We've gone from this wide-open mystery to a very, very specific question. What values of A actually make this equation true? And just like that, we have our suspects. A could be 0 or a could be 1. One of them is our culprit, and the other one is just a clever decoy. The game is afoot. All right, it's interrogation time. We are going to put each of our suspects under the microscope. We'll plug their values back into our original matrices and see if their stories line up with our central clue, that the dimension of the image of ST is less than the dimension of the image of S. First up, let's bring in A equals 0. We'll substitute 0 for A everywhere in our matrices and then do a little something called row reduction to find their rank. And remember, the rank of a matrix is really just another way of saying the dimension of its image. For A equals 0, it turns out both matrices have a rank of 2. And there you have it. The dimensions are equal. This is a direct contradiction of our main clue. The clue explicitly said the dimension of ST's image had to be less than S's. So, case closed on A equals 0. This suspect's story just doesn't check out. Okay, let's bring in our final suspect, A equals 1. We run the exact same procedure, plug in 1 for A, do our row reduction, but this time we get a totally different result. The rank of ST is 2, but the rank of S is 3.
And there it is. That's the moment. With A equals 1, the dimension of ST's image is 2, which is in fact less than the dimension of S's image, which is 3. The clue is satisfied, the case is cracked, we've found our culprit. A equals 1.
Okay, so we've got our guy, but the investigation isn't quite over yet. Now that we've identified our main culprit, A, we can go after their accomplice, the transformation T. T was part of that combined operation ST, but up until now, its identity has been a total mystery. So, the connection between these transformations is actually pretty straightforward. The matrix for ST is just the matrix for S multiplied by the matrix for T. With a little bit of algebraic shuffling, we can isolate T. All we have to do is multiply ST by the inverse of S, which is basically the mathematical way of undoing what S did.
From here, it's just a matter of following the steps. We already know S is invertible because its rank is 3, a full house. So we just calculate its inverse, multiply it by the ST matrix, and boom, just like that, the identity of our accomplice, T, is revealed.
But hold on, there is one last really cool piece to this puzzle. We're going to prove that the kernel of T is the exact same as the kernel of ST. The kernel is a special set of vectors that get totally squashed to 0 by a transformation. This final step is going to show us just how beautifully interconnected everything in this mystery really is.
So what even is a kernel? Honestly, the best way to think about it is like a transformation's personal black hole. It's the collection of all the vectors that, when you apply the transformation, get completely sucked in and squashed down to the 0 vector. Anything that goes into the kernel, poof, it's gone, mathematically speaking.
Okay, the logic here is it's a thing of beauty. So let's walk through it. First, it's a known fact that the kernel of T is always contained inside the kernel of ST. Now, we use this really powerful tool called the rank nullity theorem. It says the dimension of our space, which is 3, has to equal the rank of ST, which we found is 2, plus the dimension of its kernel. A little subtraction tells us the kernel of ST has a dimension of exactly 1. We also happen to know T isn't invertible, which means its kernel has to have a dimension of at least 1. So think about it. How can a space that's at least one-dimensional fit inside a space that's exactly one-dimensional? Well, the only way is if it's also exactly one-dimensional. And if they have the same dimension and one lives inside the other, they have to be the exact same space. It's airtight.
And with that, the case is officially closed. Let's just take a quick moment to look back at the investigative techniques that helped us crack this whole linear algebra mystery open. You know, this case was really a masterclass in detective work, linear algebra style. We saw how a simple clue about dimensions led us straight to a determinant of 0, which then handed us our suspects on a silver platter. We used the tried and true method of row reduction to interrogate them and find our culprit. And finally, the rank nullity theorem gave us that elegant conclusion that tied it all together. These are the exact tools that power everything from computer graphics to data science. We solved this whole thing just by following the clues using the pure logic of linear algebra. It just goes to show you that with the right tools, like determinants and ranks and kernels, you can unravel even the most tangled puzzles. So the real question is, what other mysteries are out there, just waiting for us to solve